Welcome back, friends, to another session of fluid mechanics and rate processes. We've been looking at potential flows. So first we started looking at some very basic flows. Then we got to superposing some basic flows into slightly more complicated flows. We looked at the doublet. We looked at the Rankine half body. And today we are going to look at a very special flow past a circular cylinder. So again, we'll start with the potential flow and then see why it does not replicate some of the features of a real flow. So we'll say make some comments about that as well. Flow past a circular cylinder. And the first thing we want to look at is the potential flow. Just to remind you, the potential flows that we are looking at are inviscid, irrotational, and in this course we are mainly focusing on incompressible and also steady. Okay, so it's very, very special cases. Okay, so we are going to first talk about superpose uniform flow and doublet. I showed you in the last session that we could get a doublet by bringing in a set of source and sink. So the idea was that the source squirts out fluid, the sink collects it, and they become very close to each other. And then the strength also increases to a very large extent, such that the strength times the distance between them is a finite quantity. That gives rise to a doublet. So here's a uniform flow. This is aligned with the x-axis. And here it is, I have the axis itself, x and y. And I'm going to put a doublet here. So the doublet, as we so this is the doublet and uniform flow. Okay, so the resulting phi that I could write is the superposition of the uniform flow. So this phi, if you recall, was given as ux, okay, and the psi can be written as u times y. And for a doublet that is located at the origin, I had given you the expressions. The phi is given as m by r cosine theta. So the polar coordinates are more suitable. And similarly, the stream function was minus m by r sine theta. Okay. Now, if I want to do a superposition, I simply have to add the two phi's and the two psi's. So let's do that. Phi would be given as u times x for the uniform flow plus for the doublet m by r cosine theta. And the stream function is given as u times y plus, in fact, I would have a negative sign here then, m by r sine theta. That's it. So I can now get the potential and the stream function for the combined flow. If I want to get the equipotential lines, I have to put this function as a constant, and by changing the value of the constant, I would get different potential lines. Similarly, to get different streamlines, I would take the right hand side of this function and keep that equal to constant. Different constants would give me different streamlines. Okay, let's work on this a little bit. So first I would like to get the two components of velocities. So if I look at v, I could write that as Vr Er plus V theta E theta. And we have already talked about our convention. The convention is that if this is my axis, the x and y axis, and I look at any point where I am interested in the speed, and this is my r, the vector, this is theta. So the decomposition is such that I can talk about a unit vector Er, which is radially outward, and then the theta, E theta, is a unit vector in this direction, and Vr and V theta are the velocity components in this direction. So I could get a velocity vector in the polar coordinates, or I could also get them in the Cartesian coordinates as Vx and Vy. Okay. Now what I'll do is, I'll try to estimate the phi, for example, and then get the velocity component from that. So Vr, for example, is given as del phi by del r, and V theta is given as del phi by del theta, with of course a 1 by r in it. All right, so this would give me del by del r of, this is my phi, ux plus m by r cosine theta. So I could write this as u times x is actually r cosine theta plus m by r sine theta. And similarly, this one would be 1 by r del by del theta of u r cosine theta plus m by r sine theta. I am sorry, I made an error here. This should have been cosine theta. Okay. So I am looking at phi, which is m by r cosine theta. Okay, so Vr, if I work it out, I could take cosine theta outside and do a derivative with r. So I would get the following: u times 1 minus m by r square and u cosine theta. And likewise for V theta, I would be able to get, this is minus u 1 plus m by u r square sine theta. Okay. So these are my components of velocities everywhere. Okay. How about the stream function? Because that would help me draw the streamlines. So I could also get the stream function, and the stream function here would be essentially u times r sine theta minus m by r sine theta. And this equal to constant would lead to streamlines. I'll be using this. So let me put this on the blackboard. Okay, so the first thing that we want to understand is, what about the stagnation points? Does this flow have any stagnation points? So first question is, the stagnation points. So these are points where Vr is 0 and V theta is 0. So the fluid comes to rest. Intuitively, you can feel the following. There is a doublet which is present at the origin, and then there is a uniform flow. As you know, the effect of the doublet is varying as 1 by r. So if I go far away, I should not see an effect of the doublet, and therefore I should just see uniform flow everywhere. But as I get close to the origin, of course the doublet is going to be significant. So the stronger my m, the stronger the strength of the doublet, the larger would be the region where the doublet would be important. If m is small, then of course compared to u, then I would have a smaller effect of the doublet. Okay, so the stagnation point essentially is also representing what is the effect of the doublet on the flow. So there are many effects, this is one effect. If the doublet is not there, then clearly this flow does not have any stagnation point. It's a uniform flow everywhere. So let's put in Vr and V theta equal to 0. Okay, so these are the expressions, and so let me call this as 1, let me call this as 2. So Vr equal to 0 gives me that r square is actually m by u, or I must have cosine theta equal to 0. Okay. The second equation tells me that my r square is equal to minus m by u and sine theta is 0. Okay. Okay. So clearly from this we can see that sine theta must be 0. Obviously you cannot have r square to be minus m by u. Okay. So if sine theta is 0, so then this condition implies that theta is equal to either 0 or pi. Okay. And clearly if I put theta equal to 0 or pi, then of course I don't have cosine theta equal to 0. So this condition I don't use, and I get r square equal to m by u. So I will now define m by u as r square, okay, and of course r is equal to plus minus r, okay, for stagnation point or at stagnation point. So essentially what I am saying is that if I draw the axis, this is the x-axis, this is the y-axis, then there are these 2 points which are the stagnation point, and they are located at RR. And of course there is a doublet in here, and so on. And of course there is a uniform flow coming in. What about the stream function? Let's calculate psi at the stagnation point. So this is my definition of the stream function, and clearly if I put the r equal to capital R and theta equal to 0, then I see that the stream function goes to 0. So what this means is that the streamline that passes through the stagnation point corresponds to psi equal to 0, and that we will call as the stagnation streamline. So to get the stagnation streamline, all I have to do is put psi equal to 0, okay, which means that I need to put this function equal to 0, and that would be simply ur times 1 minus r square by r square sine theta equal to 0. So if I somehow evaluate this function, then I get the stagnation streamline. Okay, so this will have different solutions, and the way I can look at it is I can take a particular value of r and evaluate the theta at which this function is satisfied, or conversely I could take different values of theta and see what is the value of r. In any case, if we do that, we are going to get the stagnation streamline. So maybe I should draw it with a red color. So my stagnation streamline would actually be a circle. This would be my stagnation streamline. Okay, you can check. All right. And the streamlines around it would of course be not the stagnation streamlines. You can see they would actually look something like this. And on the outside, they go around. Although I have not drawn it, but there is symmetry about y-axis. Okay. So the flow apparently is reversible. Okay. So whatever is the flow I get in the forward direction, okay, about x equal to 0, then I could just take a mirror image and get the same flow on the other side. Okay. And in particular, I have drawn the stagnation streamlines, and in white color are all the other streamlines. Okay. Let's look at how I define my Vr and V theta now in general. So having used this relation that r square is m by u, so I can rewrite 1 and 2 as the following. So Vr is given as essentially u times 1 minus r square by r square cosine theta, and V theta is given as minus u 1 plus r square by r square sine theta. Okay. Now I could ask myself, what does this flow resemble? So as we have discussed before, that by definition a streamline means that flow does not cross it. So I could take any of these streamlines and replace that with the surface of a solid body. What I will do is that I will take this streamline, which is the psi equal to 0 streamline, the circle, and replace this circle with a solid body. So replace circle with solid body. And what that does is, then I am able to have a model of flow past a circular cylinder. But mind you, this is the potential flow, where the fluid is supposed to be inviscid. So the argument that is being made is that if I replace this with a solid body, then even though the doublet was there in the initial model, and of course it still exists as far as my definition of velocity, potential and stream function is concerned, but this mathematical expression now resembles as if I am looking at flow past a circle. In fact, you could also argue that if I am only interested in the upper plane, then this models flow past half a cylinder. So if I had some kind of a dome, okay, and I wanted to study what is the flow over a dome or a hut in the context of a breeze or a storm, I could use this model. Okay, it has its own limitations, but nevertheless it's a fluid dynamics model. For that matter, I could even take some other streamlines and replace that with the surface of a solid body. But we are interested in a cylinder, so we'll do that. Now the next thing we want to ask ourselves is, what about the properties of the flow on the surface of the cylinder? So surface of cylinder. So clearly we are first interested in the speed, and then we would be interested in the pressure. So let us evaluate Vr and V theta. So Vr, I would substitute R equal to capital R, and that would be 0. And V theta, as you can see, if I substitute R equal to capital R, then I get minus 2u sine theta. Makes perfect sense. Okay? If I had a circular cylinder, then what is being said is that on the surface of the cylinder, my normal velocity should be 0. Okay? I cannot have a flow going inside the surface of the cylinder. So Vr equal to 0, therefore makes perfect sense. What about V theta? So if you recall, if I look at a certain point here, okay, then this is my direction of Vr and this is my direction of V theta. So the negative sign simply implies that actually the flow would be in the opposite direction. Okay, so I would have, because my uniform flow is from left to right, so at this point in fact I should have a velocity vector pointing towards in the clockwise direction. So that takes care of the negative sign. At theta equal to 0, this is theta equal to 0, I would get Vr equal to 0 and also V theta equal to 0. So these are stagnation points. So theta equal to 0 and theta equal to pi will give me stagnation points. So theta equal to 0 and pi are special points where Vr and V theta are 0. And V theta is maximum at the shoulders. Okay. So V theta equal to pi by 2 is minus 2u, and V theta equal to minus pi by 2 at theta equal to minus pi by 2 is actually given as 2u. So this is interesting. What we are saying is that there is a uniform flow and it tends to get a 0 speed at the stagnation points, and then as the flow goes over the surface of the cylinder, okay, its speed increases from 0 to twice the free stream speed. So actually the fluid element undergoes a fairly severe acceleration, 0 to twice the speed, and then it again goes through a deceleration and goes back to a 0 speed. Okay, so that's on the surface of the cylinder. We can also use the Bernoulli's equation now to calculate the pressure on the surface of the cylinder. So having obtained the velocity field, let's now try to obtain the pressure field. So let me draw the streamlines for you, and then we'll. So this is the circular cylinder. This is the stagnation streamline. And I am not going to draw the streamlines inside because we have replaced it with a solid body. So this is my origin and this is the radius of the cylinder. And the streamlines outside, they go around and So they are symmetric about the y-axis as we have already discussed. And so on. Okay, there is no flow separation because there is no viscosity and the flow, as we said, is perfectly symmetric about the vertical axis. Let's call this as point A and this as point B. So A and B are stagnation points. In fact, often A is referred to as the front stagnation point and B is referred to as the rear stagnation point. Okay? Okay. Now we are going to find out the pressure on the surface of the cylinder. So we'll apply the Bernoulli's equation. We are going to neglect the body forces, okay, that gravity, for example, will not be used. So the Bernoulli's equation for this flow, because it is an irrotational flow, it can be applied between any 2 points in the flow. So we'll apply on the surface of the cylinder and a point far away to the left in free stream. Okay. Bernoulli's equation tells us that V square by 2 plus P by rho, this is constant everywhere. Okay. So let's apply first to a point far upstream. So I would get V as simply U square by 2 and then I have the atmospheric pressure by rho. This should be applicable to a point, let's say this is a certain point that I am interested in over here at point P. What about the speed? The speed is given as Vr square plus V theta square equal to V square. So this I will write as V square plus V theta square by 2. And this is P at the theta that I am interested in by rho. Now on the surface of the cylinder, my Vr, as you know, is 0. And V theta, as you know, is given as minus 2u sine theta. So for the pressure on the surface of the, so P theta by rho is simply given as U square by 2 plus the atmospheric pressure and then this quantity over here, which you can see I would get 4 U square sine square theta by 2. Okay. I would like to define Cp as the pressure coefficient. And that we are going to define as the pressure at a certain point minus the pressure far away, and I am going to refer to that as the atmospheric pressure. Some people would also represent it as P infinity, it is just a notation, divided by half rho U square. Okay. So I can do the juggling here a little bit, okay, and what I would be able to then see is that Cp for this expression would turn out to be 1 minus 4 sine square theta. Okay, so you take care of a few factors here and there, and this is the expression for Cp that we will see. All right. How is theta measured? This is how theta is measured. Okay, so theta equal to 0 is actually the rear stagnation point, and theta equal to pi gives me the front stagnation point. Suppose I am interested in theta starting from the front stagnation point because that is more convenient. So let me define this angle. So the flow is coming like this, and this is a point that I am interested in. So this is theta, but I am interested in this angle phi, and phi is pi minus theta. From this expression I can see that Cp at phi is also 1 minus 4 sine square phi. Okay? Because of the symmetric nature of the flow, whatever pressure coefficient I get at this angle, I would get the same pressure coefficient at a mirror image on the windward side of the cylinder. So it doesn't matter where I measure my theta from as far as pressure is concerned. I could measure it from the positive x-axis, or in fact I could measure it from the negative x-axis as is shown here. Okay? So Cp in terms of theta and in terms of phi is identical. All right, now we can plot how the pressure distribution looks like. So I will now assume, okay, for ease or convenience, use theta from front stagnation point. Instead of phi. Okay, so I will not use phi because theta is a better quantity that we are used to. So just to keep things very clear, this is what we are saying. That's the flow, uniform flow, U. This is my x-axis, that's my origin, and I'm going to think of a point P here, and this is my theta. So theta equal to 0 now is the front stagnation point, and theta equal to pi is the rear stagnation point. So let me number these. So this is A, B, maybe I'll call this point as C, and maybe I'll call this point as D. Cp is given as 1 minus 4 sine square theta. Let's plot this. This is theta and this is Cp. And I have to plot 1 minus 4 sine square theta. The maximum value of this function is plus 1. So this is plus 1. The minimum value of this function is minus 3. So minus 1, minus 2, minus 3, somewhere here. Let me draw here some reference lines. This is theta equal to pi by 2. This is pi, 3 pi by 2. This is 2 pi. If I plot this function 1 minus 4 sine square theta, then I will be able to see that at pi by 2, I get a value of minus 3, So the graph that I would get is something like this. Okay. And if I had to mark the points A and B, so A is the stagnation point, so this is point A. The point B is the rare stagnation point, so this is point B. This is again A at 2 pi. Point C is on the shoulder, so it's at pi by 2. So this is point C. And this here is point D. Okay. So if you look at the flow from A through C, a fluid element as it travels, remember this is a steady flow. So when I look at a streamline on the surface of the cylinder, it is also a path line, it is also a streak line. So as this fluid element goes from A through C, its speed increases. At A the speed is 0, at C the speed is twice the free stream speed. We have already shown that. What happens to the pressure? The pressure coefficient goes from +1 to -3. So a large pressure to a very low pressure. Okay. So this is the region of, I would say, favorable pressure gradient. On the other hand, when the fluid element goes from C to B, here it has the highest speed and the lowest pressure, so Cp is -3, and it is now moving into deceleration, so the fluid element reduces the speed and the pressure increases back to +1 for a potential flow. So it is now moving in a region where the pressure is increasing. So C through B, this region is actually the region of adverse pressure gradient. I hope you are not confusing this with gravity. Okay, we have not accounted for gravity in this flow. So there is no gravity here. Okay, so you cannot really use this analogy with a hill, okay, where the potential energy is increasing and then decreasing. It's very tempting to think of it that way, but this has nothing to do with the potential energy, it has everything to do with the pressure. So I repeat, the element, the fluid element over here has the lowest kinetic energy and the highest pressure. As it moves, the Bernoulli equation tells us that there is a transfer from the kinetic energy of, there is a transfer from the pressure of the fluid element to its kinetic energy, and at point C it has a very low pressure and a very high kinetic energy. And then it again goes through that cycle and loses its kinetic energy by the time it reaches B. Okay. We can also show this pictorially, that how does the pressure distribution on the cylinder looks like, and it's a little bit educational. So let's do that. So I will draw the cylinder here. These are the quadrants. The flow comes in like this, and I want to show the Cp pictorially. So at this point the Cp is +1, so I am going to put a cross here, that is the value of Cp. On the rare stagnation point again Cp is +1, so I am going to draw an arrow here. So the pressure is unique pressure, so if there is a fluid element here, then the pressure actually goes radially inward, okay, it is of compressive nature, so it pushes the cylinder inside. What happens here? Over here I have a Cp of -3, so let me plot 3 units here. So this is the Cp I get here of -3. and this would be actually going radially outwards, and likewise on the lower surface as well, I would get something like this. So if I look at just the upper surface of the cylinder, the pressure goes from a positive 1 to a negative 3 over this span of theta equal to 0 to pi by 2. There is an angle at which Cp is 0, this point over here. And in fact, I can calculate that. So I can ask myself, if Cp is 0, that means at 1 minus 4 sine square theta naught, then theta naught should be sine inverse of a half. Okay? And that would give me plus minus 30 degrees. So actually this angle is 30 degrees. In fact, I can plot that here. So at about 30 degrees, I would have 0 Cp. And now my picture would look something like this. And if I had to draw the vectors, so these pressure vectors are going to be in the radial direction. So this is the pressure at this point. Let me try to draw a radial line. So this is the pressure at this point. This is the pressure at this point. There's a Cp of 0. And then here the pressure actually is inside. And then again so I hope you are able to get a sense. So the picture is symmetric with respect to this axis over here, the vertical axis, and it is also symmetric with respect to the x-axis. Okay. So what we are seeing is that this particular cylinder sees a very high pressure at the stagnation point, the front as well as the rear. It sees a very high suction at the shoulders. So these theta equal to pi by 2 points, we call them as shoulders. So let me write that down for you. This is called as the front stagnation point. This point here is often called as the rear stagnation point. Sometimes it is also called as the base point. And this point here is actually called as the shoulder of the cylinder. And now this picture shows you very clearly that as a fluid element goes from 0 to pi by 2, it is going in a favorable pressure gradient. Okay? And then as it goes from pi by 2 to pi, it's an adverse pressure gradient. I can now estimate what is the drag and lift on this body. And you can see that there is no viscosity, so there is no viscous drag. As far as the pressure is concerned, the pressure is symmetric about the x and the y axis. And therefore, I have to conclude that CD is 0 and CL is 0. This is the drag coefficient, this is the lift coefficient. Okay. So drag is the force defined in the direction of the velocity, and lift is the force acting on a body normal to the direction of velocity. In this case, the flow is along the x-axis, so the lift force will be in the positive y direction, and the drag would be in the positive x direction. Both are 0. And this is what actually troubled a lot of people. So in fact, there is this famous paradox by a French mathematician. So the D'Alembert's paradox. which was given in 1752, which said that inviscid flow predicts zero drag, but drag is finite, and in fact it is substantial at large RE. So the confusion that people had is the following, that if I have a very large Reynolds number, then in principle I should be able to neglect viscosity. But when I neglect viscosity, then I get this very interesting pressure distribution which is symmetric, which actually leads to zero drag. Okay, so therefore this theory is not explaining the reality. So people went on to figure out what's wrong with this theory. And of course it turns out that even though you have large Reynolds number and you are tempted to assume that inertial forces are very large compared to viscous forces, we have already discussed this, you cannot throw away the viscous term inside the boundary layer. So close to the body, there is a thin layer where the viscous terms must be retained. So therefore, Prandtl, the famous fluid mechanicist, proposed the concept of boundary layer to explain this, to explain or resolve this paradox. So I want to spend some time on what are the modifications to this simple flow on flow past a circular cylinder when you include the viscous effects. Okay, so we have seen everything we wanted to know about the potential flow. We have seen the streamlines, we have seen the pressure distribution, and we have seen the lift and the drag that arise out of it. What about a real flow? Okay. So let me give you some pointers, and I will try to draw some diagrams here for the real effect of the flow. So first, a few preliminaries.